Hey everyone, Big Mac here. How's it going? Welcome back to my favorite pre-calculus test questions. So again, what is this series of videos that I've been uploading? Well, these are a series of questions that I used on actual midterms for a college-level pre-calculus class. So again, these are supposed to cover the basic materials of algebra, trigonometry, and stuff, things that were needed in order to properly conduct a full course in calculus. So that being said, I assume the students have through Algebra 2 skills and, at least some recollections of things from geometry on an as-needed basis. So what are we doing on this exam? This midterm covered everything from exponential functions, logarithmic functions, talking about half-lives of properties and, how fast would it take for your investment to double. We also then started getting into our basic discussions of right triangle trigonometry, or SOHCAHTOA, all the basic traditional formulations for 2D triangles and stuff. So here are a couple of questions that I came up with during this midterm that I found really interesting. Some of them were, I thought, pretty easy, and yet people still managed to find ways of messing things up. So here we go. This was our first question. The math magician, floating 20 feet above the stage, is ready for his final act. Two spotlights, a total distance 40 feet apart from each other, point up towards the magician. So the angle of spotlight measure A is 53 degrees. So the question is, what is the angle of spotlight number B? So at this point, I was going to ask students to just round to the nearest tenth of an answer, or at tenth of a degree. So that being said, we're going to have to recall some basic right triangle properties, going on with our right triangles, our particular angles. How does that relate to all of our different trig functions? So again, if we have a generic right triangle, we know it's a right triangle because we have a little square indicating that we have a 90-degree angle. For a particular angle, other angle theta, we can relate the different trigonometric functions to the lengths of the sides of the triangle. So there's the adjacent side, which is the leg that is next to the angle. There is the opposite side, which is the leg opposite of the angle, naturally. And of course, the longest side is still the hypotenuse, however you wish to spell it. So of course, our three most common trig functions, we have the sine function. We can describe this first angle theta as the sine of theta is the opposite length, or over the length of the hypotenuse. Our cosine function is the length of the adjacent leg over the hypotenuse. And our tangent function, tangent of theta, we can either write that as just the ratio of the opposite side to the adjacent side, or as sine theta divided by cosine theta. So that being said, for this right triangle trigonometry problem, we had to break this up into a couple pieces. We know we have two different spotlights. We saw two different triangles right off the bat from our question. So let's try and work on those one piece at a time and figure out how to get our answer that we're looking for. So focusing on just the triangle on the left, we were already told that the height was 20 feet. This was on one version of the exam. On another version, I had it as 30 feet, just to make sure that different students were not trying to look at other people's answers. So we also knew that we had an angle of 53 degrees in this example. We have a side length that we need to figure out. I'm just calling it A here, nothing to do with the angle A originally mentioned. So we just have to figure out what this length of our triangle is. So if we need to use a trig ratio that incorporates the opposite side of our 53 degree angle to the adjacent side, that suggests that we should use the tangent function. So that being said, we know that our tangent function of our angle, which is 53 degrees, we know that that is a ratio of 20 divided by the length of that other side. So fortunately, students had use of calculators, so they could just plug in what is the tangent of 53 degrees, so to a few decimal places, and I hope that students would at least carry it out to a few figures. Looks like we get about 1.327, plus a little bit more naturally. So if we know that this 1.327 is 20 divided by the length of our other leg, then we can just use some basic algebra and solve for the value of A by itself. So that being said, A is 20 divided by the tangent of 53 degrees, which again to a few decimal places comes out to about 15.07. So that being said, we've got this left triangle set up now. We know that our person is 20 feet up to ground. We now know that from the spotlight to where our magician is, at least on the ground, is 15 feet long. But we were also told that our spotlights were 40 feet apart from each other. So that being said, if this part was 15.07, then our other segment here had to be 40 minus that, or about 24.93. So now we've got we still have this height of 20, and now we know that this that this side, which is adjacent to angle B, is about 24.93 degrees. So that being said, we now have another trig ratio that we need to solve for, but we have the opposite side and the adjacent side. In this case, all we have to do is find the angle. So again, using our SOHCAHTOA mnemonic, we know that opposite and adjacent relates back to the tangent function. So we know that the tangent of angle B has to be the ratio of 20 divided by 24.9289. Again, rounded to a couple decimal places. So this comes out to about 0.8023. So we know that there is some angle B such that when you plug it into the tangent function, tangent of B is about 0.8023. So of course, in order to find that value of the function, we take the inverse tangent function, or the arctan function. So again, the students had calculators, they could just plug that in. And from there, they should have determined that their final answer was 38.7 degrees. So again, I thought that this was a pretty straightforward example, utilizing our right triangle formulas, focusing on the tangent, but we had to use the tangent related to the sides. We also had to use the inverse tangent function to determine a specific angle. And how did students do? For the most part, students did pretty well. But that being said, there were just a lot of little things that surprisingly, made this problem hard for students. So looking back at our first question, a lot of students assumed, hey, these triangles look exactly the same. And while I appreciate that my art skills, were not terrible, this led some students to believe that everything was drawn to scale, which, knowing me and my limited MS Paint skills, no, things were definitely not drawn to scale. So that being said, a couple students were just like, it looks like the other angle should also be 53 degrees. And of course, they got that answer wrong and got no credit. Another answer that was confusing me quite a bit was that some students said that the answer was 37 degrees, which is pretty close to the original answer. So I was wondering, did they do some kind of rounding error or something else that was going on? Well, most students were saying, okay, this angle is 53, and this angle is 90, and this angle, we don't know what it is, but we know that the angles of a triangle have to add up to 180, so then this other one's got to be 37. Totally bypassing everything that we had just talked about for the last 2 weeks. And no, I'm not going to try and trick them like that by just shoving a random pure geometry question in there. I think people were just trying to find an easy way out instead of trying to, run through the trig ratios using their calculators. Because again, if students are not comfortable using the functions on their calculators, then they're not going to be able to understand what their answers are, or what the answers are popping out on that their calculators are saying. So yeah, some people said 37, and I was like, no, you're not thinking about this right at all. Some people, when I mentioned that the two spotlights were 40 feet apart, some people thought it was from angle A up to the magician, and then back down. So they were trying to relate everything back in terms of the hypotenuses of the two right triangles. But if you do that, then I think you get some weird ratios, possibly that this side was longer than 40, or very, very, very long, and that this side was very, very, very short. I don't remember the exact number. But again, that just ended up with some really weird things that were appearing in terms of that. So I gave mostly credit because, again, I wish that if the student had been confused, they could have just come and asked me about it, but whatever. So the one that upset me the most was that students were able to follow through everything in terms of the right triangles, but then when it came to finding the inverse function, not so good. So if we have that the tangent of angle B is about 0.8023, like I said, well, that means that B is 0.8023 divided by tan. This one hurt a lot. Because, one, this makes me think that the student thinks tangent is its own thing, and then tangent times B is 0.8023. So then B, you just divide both sides by tangent, and you get 0.8023 divided by tan. What? Tan of what? Again, our functions need an input, so you can't just divide by the function, without it meaning anything, in order for it to mean anything. So for students who were just like, oh, it's 0.8023 divided by tan, I was like, no. I knocked off quite a few points for that, because they obviously did not understand what was going on here with our inverse tangent function, and again, some students were still confusing the inverse function with the reciprocal of a function. So again, that's probably where part of these issues were coming from. Lastly, there were just some rounding issues, and that led to a loss of accuracy, sometimes up to within a degree, actually. So if students truncated their answers too early, like going back up here, if they had just said that this was 15.1, and then from there this becomes 24.9, and then from here that you get a rounding of maybe 0.81 or 0.800, that's going to change your answer a little bit. Not a whole lot in this case, but still enough for me to look at your final answer that is not quite 38.7. And, usually I was pretty lenient. I just took off maybe 1 point for rounding issues. In this example that I drew here for you guys, I tried to keep things to like at least 4 places after the decimal value. Hopefully students would do that, or just leave the entire value inside their calculator and then do 20 divided by answer, something like that. And then lastly, this is a regular trig problem involving degrees. Some people left their calculators in terms of radians, and then weird stuff happened from there. You started getting negative lengths and other things, kind of like in this other example where people were using the hypotenuses accidentally. So again, weird things, but I have to make sure that students understand how to use their calculators. And I can spend a little bit of time in class doing that, but not a whole lot. And going on to question number 2, we had a couple of exponential functions where we had exponential equations where we had to try and solve for our particular answers for x. So we had to give the exact answer, using an approximation. It was not going to work in this case. So we had a couple problems here. These were just 2 of my favorite ones. So if we have 7 to the x is equal to 7 to the 0 power plus 7 to the first power plus 7 squared. So we need to find the exact value of x that satisfies this equation. Our second equation that we have x cubed times e to the x minus 9x times e to the x. And we're seeing that that equation is equal to 0 on the right side. So how do we kind of go about these kinds of problems where we have exponential functions? What are the properties that we can do with these things? What about their inverses? What can we do with logarithms in trying to solve these equations? So in general, if we have an exponential function with some base a, assuming that a is a positive number. So if we have a general function a to the x, our domain is all real numbers. That means we can plug anything in for x. Our range, for the original base functions is 0 to infinity. That means we have a horizontal asymptote at y equals 0. And of course our function does shoot off towards positive infinity as well. And of course, following our traditional ideas of when we multiply exponents together and stuff like that, we know a couple of basic properties. If we have a to the x power times a to the y power, then we know that we can actually add the exponents together. So we would have a to the power of x plus y. So an easy way to think about this is if we had a squared times a cubed, so that's a times a times a times a times a. So of course that's going to be a to the 5th power, and 5 is 2 plus 3. In a similar way, if we have a to the x power, and then that whole thing is to the y power, we can actually multiply our two exponents together, so we'll have a to the x times y power. So again, if x is 2 and y is 3, we have a squared times a squared times a squared, so 2 plus 2 plus 2 is 6, which is 2 times 3. Likewise, the inverse function of an exponential function is its logarithm. So the inverse would be y equals logarithm with a base of a, and then given our particular value x. So the most common uses of logarithms involve either the natural base, which is base e, or logarithm base 10, which sometimes is just written as log. Of course, different textbooks will use different notations for that. So what are our main properties of working with logarithms? Well, if we have the logarithm base a of a product, it turns out that we can actually split that up into a sum of two different logarithms. So the logarithm of x times y becomes the logarithm of x plus the logarithm of y, all with respect to their base a. Likewise, if we have log base a of x to the y power, so we can pretty much default that back to the previous example. So that's basically the log base a of x times x times x times x, a number of y times. Well, that just defaults to the first example up here. So then we would have log of x plus log of x plus log of x plus log of x, y times. So thus we can simplify this as y times the logarithm base a of x. So normally when we describe this in class, we talk about, oh, the exponent kind of just pulls out in the front and everything is happy. So how can we actually solve these particular equations using some of that information? Well, admittedly, this is, for our first equation, is a very long-winded approach, but it still works, definitely. So our idea is that we want to take a logarithm on both sides, and fortunately, for our original equation, 7 to the x equals 7 to the 0 plus 7 to the first plus 7 squared, we can take any base we want. So if you wanted to take logarithm base 7, that is fine. If you wanted to use a natural log or log base 10, because your calculator has those buttons, and that might make a little more sense for you, you can do that as well. So in this example, I just quickly used the natural logarithm. So taking the natural log on the left side, we have natural log of 7 to the x power. On the right side, we have the natural log of that sum, 7 to the 0 plus 7 to the first plus 7 squared. So following our properties of logarithms that we just talked about, we could actually bring out this x out in front. So the natural log of 7 to the x is the same as x times the natural log of 7. On the right, we had the natural log of these three things, so let's just add them up. 7 to the 0 is 1, 7 to the first is 7, 7 squared is 49. You add those up, you get 57, so we're going to take a natural logarithm of that. So we know that x times the natural log of 7, which is just some number, is equal to the natural log of 57. So solving for x by itself, we can divide both sides by natural log of 7 and come up with our final answer of the natural log of 57 divided by the natural log of 7. Using a change of base formula, we could reconvert this back into just base 7 as the logarithm base 7 of 57. So if a student was able to just easily recognize we have 7 to the x equals 57 from the very beginning, and then just go directly to the answer in this format, x being log base 7 of 57, I was perfectly fine with that and gave them full credit. That being said, the most common wrong answer was 3 for this problem. So I'll explain why in just a little bit. For our second equation, we had x cubed e to the x minus 9x e to the x equaling 0. Students kind of were not sure what to do with that e to the x. Some people tried, multiplying things together, so you had like x e to the 3 plus x power. Weird stuff started happening, but if we were going to follow this in a more methodical sense, we can solve this like we would any other equation. Can we factor things out? We've already got a 0, 1 on one side. Can we factor this out to a product of things that would go to 0? So in fact we can. We know that both terms have an e to the x, and we can pull out one term of x from both parts as well. So we can factor out x times e to the x, and then after we factor that out, we still have x squared minus 9 equaling 0. So x squared minus 9 is a basic quadratic. We know how to factor that even further. X squared minus 9 factors to x plus 3 times x minus 3. So now we've got a product of four things. We have x times e to the x times x plus 3 times x minus 3. And we know that the product of these things has to be 0. So using our old-fashioned zero product rule, we know that at least one of these things is 0. So when is that possible? Well, the first thing, x, is 0. Okay, pretty straightforward. For our second part, e to the x is 0. Wait. Our third part, x plus 3 being 0, or our fourth part, x minus 3 being 0. So three of these are pretty straightforward. We have x equaling 0, x equaling negative 3 from this equation, x equaling positive 3 from this equation. But think about what we talked about. If e to the x is 0, that would mean that it crosses the x-axis. And yet our traditional function, just our basic e to the x function, in fact any regular exponential function, does not cross the x-axis at all. So in fact there is no solution from e to the x equals 0. So we don't have to worry about that. So our final answer was just 0 and plus or minus 3. So how did students do on these questions on just the strict algebraic solving things? Pretty hit and miss. So on the first one, people did fine. I accepted either form of the answer that students would write, either using it in log base 7 or using a different log and then writing it as a ratio. I was fine with either one of those. But the main problem was that some students made up a rule that if you have a sum inside of a logarithm, then that splits up to a sum of logs. But unfortunately, we know that this is not true. So going back to our rules, if we have the logarithm of a product, we can split them up into a sum. So looking back at what we had here, for our second line here, what some students thought they could do was they could break this up into 3 separate logarithms. So they have the logarithm of 7 to the 0 plus the logarithm of 7 to the first plus the logarithm of 7 squared. And then from that, you would either get 0 log 7 plus 1 log 7 plus 2 log 7. So the log 7s would cancel out on both sides, and you would just have x equaling 3. So of course that is not a rule. Unfortunately, that does not work in this case, and I mean there's probably some values of x and y for which it does, but as a general rule, this is not true. That was the most common mistake for the first question. For the second one, I'm not sure what happened. A lot of students kind of just freaked out when they saw that e to the 0, because they had never really tried solving e to the x equaling 0. Some people tried taking a natural log on both sides and getting, the natural log of 0 is not a nice number that my calculator is spitting out, so I don't know what to do. I give up. So among students who actually tried factoring things out, they either found the 0, maybe they just plugged it in, I'm not sure, or they found the plus or minus 3. Again, maybe they just plugged it in, I'm not sure. But that being said, most students did not factor it out all the way and try and figure out what to do. The thing that worried me the most was, some people moved the terms to both sides. They divided both sides by e to the x. They then divided both sides by x. So all they were left with was x squared equals 9. So that being said, they lost the solution of x equaling 0, and they just kind of ignored that e to the x term in hopes that it would just kind of magically go away. In this particular example, it kind of happened to, magically go away. But in general, that's definitely not a good thing to do, is dividing equation by a variable can lead to weird results. Going back to my first example, in the first video where I talked about trying to solve an inequality by dividing variables, and bad things happen from there. But that being said, overall, this test was relatively easy. I just asked some basic questions, a few word problems, some basic right triangle trigonometry, and this test, I believe, was the highest average of all of my midterms for this class. So that being said, for our next video, we're going to look at the final part of our trig course. So we start talking about trig functions in general, as well as more properties, identities, and all of those fun things. Until then, Big Mac saying, later.